Today I want to tell you something about deep learning and advanced machine learning on IoT data, and why I want to introduce why we do IoT and what we do. And the second thing is I tell you something about the latest advancement in AI and machine learning. Then I will do 2 little demos, and if we still have time, you actually can participate with your laptop and deploy something on your own and play around with it. No, you only need a web browser because it will be based on an online editing system, which I'm sure you will like. It's open source, and yeah. So I'm working for IBM Watson IoT. That's a new business division IBM found last year, and it's headquartered in Munich, so it's not so far from me. It's the first IBM headquarter outside US, and IBM did that because we see that IoT is a very, very large trend at the moment. So that last year we had 15 billion connected devices, and in 2020 we will have around 40 billion. And if you compare that with the world's population, you can see that that's a really lot of devices. And we are constantly using MQTT as means of connecting all these devices, and MQTT is an OASIS standard since 2013 and was invented by IBM 1999. That's what IBM does in the MQTT space. So we basically provide an API for more than 200 device types, and it's an open system, so everybody can write an API for his device type. So we are also in contact with hardware producers. All this data goes to the cloud using MQTT. So we basically have a MQTT broker as a service, and we care about fault tolerance and failover and scaling and all that things. And it's a publish-subscribe mechanism. And in addition to that, you can manage your devices. So you can update them, and you can, for example, only update 1% sample of all your devices, see whether they still work, and if that's the case, then you can roll out the update in batches to all the other devices. We have APIs to access the data, and you can stream it in using MQTT or HTTP, and you can also stream it out using HTTP and MQTT, and we basically guarantee the delivery. And then downstream, that's the most interesting part, we do analysis of that MQTT or IoT data, and then of course we want to create actionable insights and send actions back to the device, which we call device commands, also through MQTT and also with a guaranteed delivery model. So that's an example. As you ask if you have to use Python, you can use Python if you like. So that's an example. If you have a Raspberry Pi and a device called a SenseSet, which costs $30, and you put it on top of the Raspberry Pi, it has a couple of sensors, accelerometers, and humidity, temperature, and so on, and also some colored LEDs, which you can use to display things. And you can see here you need 6 lines of code for initialization and 3 lines of code for reading a value from a sensor and format it into a JSON object and send it to the cloud. And as you also can see here, there is a QoS, quality of service level, which is here set to 2, and that means guaranteed delivery. So once this function call returns, you are guaranteed that this data is somewhere stored securely and transmitted securely. In case you don't like the API, you can use open plain MQTT as well. And if you want to dive further into that data capturing hardware part, we are the first non-academic institution which Coursera accepted to deliver a course, so you can take this course there. And yeah, that's basically all I wanted to tell about the central nervous system of IoT, because I'm more interested in the brain part, and that's what we will cover today. So there are two means of machine learning. You can do machine learning on historic data in a batch fashion, and when it comes to streaming and real time, then you also have to do sometimes online learning. That means you take the data, you ingest the data in real time, and you update your machine learning model. And in order to perform in that use cases, you have actually to do both. So both have pros and cons. By the way, if you have questions or comments or want to add anything, just do it. Yeah. So the pros of online learning is there's a low storage cost because you don't store the data, or you shouldn't store the data, and your machine learning model can be updated in real time. But not all algorithms are supporting incremental update, and also software packages usually doesn't support it. And once you come up with a new idea or with a new algorithm, then you cannot improve it because your data is already lost because you don't store it. And the compute power has to be in line with the data rate. So in events of high data influx, you have to cope with that, and you have to increase the number of CPU cores actually processing your streamed data. On the other hand, historic machine learning, nearly every algorithm is basically invented to run on historic data. There's an abundance of software available, open source and closed source, and you can do model rescoring. In case you find a better algorithm, you can run it again in batches. The other drawbacks are that you have a high storage cost because you have to store all this data, and the model is only updated in batches, so it cannot react in real time on changes. And of course you can do like mixtures of those two approaches. In cloud-based machine learning, there are basically 4 different levels. The first is on an API level, which basically just gives you a REST API for executing machine learning tasks. I have an example for this later. And the second level is you use a pre-trained model. This can either be also a REST API or it's a kind of software package. The next level is you use an existing pipeline, but the pipeline is a pipeline somebody else built for you, and you just use it with your data. And last level is you create your own pipeline and model, and that's where we will concentrate today on. So the first level is, or example for the first level is API which we have. It's the IBM Watson Personality Insight service. It's a service where you basically just send text, and based on the text, the pre-trained model generates a personality profile of you. So that's an example of my Twitter stream. So you can just use your Twitter handle, and based off the text you send there or retweet or whatever, it creates that personality profile for me. You can also use this with emails from your colleagues. If you're interested, I can show you later how that can be done. It's really straightforward. So level 2 is you use your data. In that case, you can use an API. So that's with a mixture of the approach, but you can also score the model in a machine learning framework. And then you train a classifier with your data, and after that you can use that classifier. And in this case we have a service called Natural Language Classifier, which for example is used by a startup in Berlin, which can now automatically classify 80% of incoming emails for their clients and trigger a business process based on the class of the email. So only 20% the emails have to be treated manually. So that's a formula which is ARIMA, that stands for Autoregressive Moving Average, which is a state-of-the-art algorithm for forecasting in time series. It's only there to tell you about the state-of-the-art, because I want to tell you about what's after the state-of-the-art. That's, in my opinion, deep learning, the whole cognitive computing hype going on at the moment. As you can see on the Google Trend charts, starting 2013, deep learning really took off, and I will just tell you why. So who of you doesn't know what an artificial neural network is? Okay, who of you knows what an artificial neural network is? Okay, so I will do that a bit faster. So you can see here a very simple one. It's a three-dimensional input. So you have three input neurons, you have one hidden layer which actually learns the transformation, and then you have two outputs that can, for example, be used for binary classification. So these concepts are very old. In the 70s already we experimented with neural networks, but with more or less not so good performance. So the state of the art so far for machine learning was support vector machine or a random forest, but now they are really taking off. So just to complete this, that's the topology of one neuron. So what you see on the left hand side, you have the inputs of the upstream neurons, you assign weights to them, then you have a transfer function, in most of the cases it's a sum, and then you have an activation function, and that's basically key to neural network, the activation function, because if you don't have the activation function, this resembles in something like this. You can just ignore the subtraction terms here. It resembles in a linear regression model where you basically just sum up every input and weight it with a parameter. But if you use an activation function which is nonlinear, for example sigmoid, then you actually get a nonlinear transformation. And that's why neural networks are able to learn nonlinear transformations. We will dive into that a bit later. So what deep learning means, first of all, we just add additional hidden layers, and those are basically used to learn abstractions. So each layer learns an abstraction from the upstream layer and feeds that abstraction down to the downstream layer. That's the basic idea. If you are familiar with machine learning, what you normally do is you do some sort of feature engineering, so you do that abstraction by hand. And what we basically now experience is that using neural networks we can save a lot of time in the pre-processing. That's one example for a feed-forward network where we compress data in the middle. So in the middle of that neural network we have less neurons than the dimensionality of the input data. And if you train such a network, it can basically use for anomaly detection. I will run the example later, but the thing is, the network now has to express all the data points which it sees with a less dimensional representation, which is called code set, and that actually removes a lot of noise. And if you then reconstruct your original data from the code set, you get a very simplified representation of your data. A non-neural network example of this is singular value decomposition or principal component analysis. Singular value decomposition is used, for example, in JPEG compression, where you basically reduce the dimensionality of your image and just keep the dimensions which are really expressing something interesting, and then you reconstruct your image from the compressed representation, and you get really good compression from there. But we can use those autoencoders for anomaly detection, because if the network gets input of data which it hasn't seen before, it most likely can't be reconstructed with a code. So I will show you that later in live, but that's actually an output of the MNIST dataset. Who of you knows what the MNIST dataset is? That's from a Kaggle competition, a dataset containing handwritten digits, and the competition was to actually recognize them. And a couple of years ago the neural networks outperformed every other algorithm on that. But in this case, what the demo does is it just creates such an autoencoder from all the data and tries to reconstruct the same digit, and where it gets a high reconstruction error, those are very anomal. So on the left hand side you see all the digits which the neural network considers as normal, and on the right hand side you see all the digits which the network considers as anomal. So you can do anomaly detection with deep learning networks. The next famous example are convolutional neural networks. So basically they are inspired by the visionary system of human brains, where actually a filter just scans on small fractions of the image, and that's the first layer. And as you can see here, from bottom to top, the abstraction level is decreasing. So in the first layer you only recognize edges, and that's actually the same thing what happens in your brain. The first layer you only recognize edges. So every face I'm seeing here at the moment is a composite of many edges in my visionary system. It's the same in artificial convolutional neural networks, and you see here that on the upper layers the representations are more concrete. You can use such a network to transform it in a so-called generative model and actually learn a style and a photograph and create something like this out of it. So for the machine learning guys here, that's done by combining those two images and running gradient descent on the result, and the local minima resembles actually in such an image. I was not the first one doing that, of course. I just copied an open source example. The guy who has invented this also provided this software here. So this is run on Theano, that's a deep learning framework, and you can actually learn or create such images. That's the Golden Gate Bridge, and you can learn or apply styles from different painters, and as you can see here, it's quite impressive in my opinion what the neural network can do. A startup in Zurich which works together with us is actually commercializing this idea. So you can, it's deepart.io. You can do it for free, and also they have a paid tier. So you can upload an image and you can select a style or upload a style, and it will generate such a picture for you. They are actually running on our cloud. They like us because we have NVIDIA M60 GPU cards in our cloud, and they are using those. So a normal feed-forward neural network can basically learn any mathematical function or any transformation, okay, given you have enough data. And that's one key aspect of that new deep learning hype. You always need a lot of data. And actually in IoT, that's one thing what I like in IoT, those devices are creating a lot of data. So a feed-forward network was very bad in detecting or recognizing sequences. For example, handwriting or sound or whatever is a sequence, so they are not very good in time series. Therefore another topology is coming up in the deep learning space. Those are the recurrent neural networks, which basically have feedback loops, and that means they have some sort of short-term memory. And you can even push this further and have another topology called long short-term memory networks, which actually have memory in some of their neurons. And you can also control the learning and forgetting rate of that long-term memory, and that also becomes part of the parameter space of that network. And those are very interesting because those can be used to create a generative model as well, and you can feed Shakespeare literature into them and they actually create Shakespeare literature. So what you can see here is a LSTM network which has been trained with Shakespeare literature and actually generated that text here. You can also train it with mathematical literature. That was actually LaTeX, and he created something similar in LaTeX. You can train it with a Linux C kernel source code, and it creates C source code. But what makes them very interesting is for IoT is that they outperform the state of the art in time series anomaly detection, for example. So as you can see here, for example, on the top left chart, there is a sensor, and the green line is basically normal behavior or normal data from the sensor, and the blue line is anomal data from the sensor, and the red line on the bottom of this chart is the p value. That means if you have a high p value, the probability that the data is normal is high, and what you see here at the blue spike, it just drops to 0. Actually, the LSTM has recognized the anomaly, and that anomaly has been recognized because the neural network has been trained with normal data, and once the network sees data which it hasn't seen before, it will generate such a spike. And the interesting thing is that it can run on time series, so it can basically make use of historic data. Here's, for example, on the left hand side at the bottom, you see also data from a sensor from a normal engine, and at the very bottom from a faulty engine, and as well you see that the pattern is with your eyes very hard to differentiate whether there is an anomaly or not, but LSTM can basically tell you the score of the anomaly. Another thing what you can do with LSTMs is forecasting. So in this chart you see the blue line, which is actual value, and the red line, which is the predicted value, and as you can see, they are nearly the same. And in the table below you see also the error. So the state of the art is called kernelized regression, which has an error rate of 8.3%. Then the next thing is a feed-forward network, but what they did before feeding data into the feed-forward network, they have transformed it with Fourier transformation from the time domain into frequency domain, and you get a 6.7% error rate. Then instead of doing that, so they removed the Fourier transformation step before and just used the deep feed-forward network. They went down to 5.9. So basically the message there is you can just skip the data pre-processing because the network will learn some sort of abstraction for you on its own. And then, as you can see, the recurrent neural network goes down to 2.8%. And that's raw data they just fed into the recurrent neural network. And the very interesting property or message here is that the LSTM can learn any algorithm because it's Turing complete. So given you have enough data, you can basically learn any algorithm with that. It's a bit shocking in my opinion, but yeah. So fortunately, there are some problems. In 2009, this is an example from the Google brain, which was simulating a brain of the size of a bee with 16,000 CPU cores. In 2016, you have the same computing power in one NVIDIA Titan GPU card, and we have it already, but we are not releasing it this year. We have built a chip which has the same power in a chip which consumes 4 watts. So stay tuned for the next couple of years what happens. The chip of IBM is called True North, and one chip has 1 million neurons and configurable 250 million synapses, so that are the connections between the neurons. It's a scalable and parallel and distributed platform. There's no clock, so it's just data is just propagating through the chip. It's made of silicon, so it's a normal process. It's not something biological, but there's no clock. It's just a simulator or a hardware neural network. And currently we are building a cluster with 4,000 chips and 4 billion neurons and 1 trillion synapses. And just to give you a comparison, the human brain has 100 billion neurons and 100 trillion synapses. So we are not there, but you can imagine what will happen. No? So now let's go back to the present. I've evaluated a couple of frameworks for deep learning, and the only one which I found which is able to run on GPUs and which has support for all sorts of topologies and which can be scaled on multiple nodes is DeepLearning4j. So most of the folks now are in the hype of TensorFlow, which is also interesting, but it doesn't scale. So in TensorFlow you can't scale a neural network on multiple nodes. What you can do, you can run multiple configurations of a neural network on multiple nodes. That's useful for hyperparameter estimation, but you cannot scale a single one. And that is what makes it very interesting, especially since I'm in IBM and we are committed to Apache Spark. So that's our strategy on all that big data processing, and that runs on top of it. So this leads to the following architecture for my IoT data analysis pipeline. So I have the devices, I stream them in through MQTT, through the IBM Watson IoT platform, and then I just stream them further into Spark streaming, and from there on I can use any sort of algorithms, whether it is a MLlib, which is some sort of a built-in library in Spark, or whether it is a third-party library for time series analysis, or whether it is DeepLearning4j. That's something I wanted to remove. That was another talk. Sorry for that. So now I want to try something with you, and I'm not sure whether it works. It didn't work before, but let's take the chance and try it. So actually what will open if you open this link is a little web page. If you open that on your mobile device, it will access the accelerometer values of your sensors in the device, and through an open source JavaScript MQTT library it will send the data to the IBM Watson IoT platform, which is the MQTT broker. And then the basic game is that you just shake the device, and I'm calculating the energy you produce. I will show you later how I do that, and the one who creates the most energy just is the winner. But it didn't work before, but I don't know whether it was the wireless, which is not so stable here in my opinion, or that you can decide. Yeah, sorry for that. So that's the link again. And it's limited to 20 participants, so the 21st won't be captured. That's because the service is in our cloud. So we have a platform cloud called IBM Bluemix, and there's for every service we have there's a free tier. And in the case of the IoT platform, the free tier is limited to 20 devices. It's the same infrastructure, but just limited to 20 devices. Okay. So for device ID, you can choose anything. I recommend 8-character ID, which you can remember because we want to find the winner. And the important things for password, you have to use a lowercase 8-digit password. Just type anything, you won't need it anymore. It's a bit a crappy application. I didn't write it, but yeah, and it even doesn't give you an error. So if there is an error, it just doesn't work. So please be careful. And let's double check. I always get this error message here, which is not a good sign, but basically I just show you what I do here. This is Node-RED. So Node-RED is a data flow editor written in JavaScript running on top of Node.js and open sourced by IBM. So you can go to node-red.org, use it in the cloud. So in IBM Bluemix we have it as a service. You just push a button and you get it. But you can also install it through the NPM manager of Node.js and use it from there, or even run it on a Raspberry Pi or something. So this is a connector to the MQTT broker, and I see some of you already are sending data, so but I don't see the data. That's very, very unfortunate, because okay. Yeah. Yeah. I take the accelerometer values, so the X, Y, and Z axis, and also the angle of your device. But yeah, but that I'm not using for my analysis. I'm only taking the accelerometer values. But I think you can stop all your effort because I have some connection problems, unfortunately. You are connected? Okay. Good. Yeah. So let's see. Yeah. Aha. Actually, you are sending now the accelerometer values of your cell phone to the cloud. The accelerometer. So that's the, yeah. So if you shake it hard, you will create big values. If you shake it soft, you will create small values.
Yeah, but still,
Yeah, that's a sample. So 10 times a second, it creates a sample and sends that to the cloud. Okay, so I see already 18 of you have started to create data. Yeah, no worries. Oh. Yeah, actually, if you stay until the end, I will show you how to do that on your own as a hands-on exercise. But so you can see here, that's data coming from somebody's device. For example, the one who has device DEVNL. Who's that? DEVNL? Okay. Ah, here. Okay. So please shake, and then you see here the accelerometer data is basically those three. So can you stop shaking, please? So you get no just to demo it. You get values near 0. Can you start shaking again? So you see, you should, if you are the right one, you should now see bigger numbers. I have some issues with the network because I don't see the updates anymore. Yeah, that's unfortunate here. But anyways, I was prepared for that, so I will just show you what the basic analysis is. So let's go back to that one. So in this Node-RED editor, I just subscribe to messages using the pub/sub paradigm of MQTT, the MQTT broker, and that what you see is you basically get JSON messages coming from the device through MQTT. That's the one on the right hand side, that DID RKIE 1234 blah blah. That's a nested JSON message, and what I basically do is in that flow I have a little JavaScript function in order to create a relational schema, and then I just store this data to a database. So I have the accelerometer values of X, Y, and Z, a timestamp, and your ID in the database, and that I can basically use for analysis. And because the network is so bad at the moment, I just show you how to do this in RStudio. Who of you doesn't know R? Doesn't, yeah? Who of you know R? Wow, okay, nearly everybody. So then I just, oh, I have to reopen that. I have to search that. Demos. So it's pretty straightforward. So that's a CSV file I have created from another demonstration where it worked better. So I just do the following. So I aggregate by your user ID. Yeah. I try. Here. Zoom in. That's partially true. So there is one project called H2O, which actually has an R binding. The only drawback, there are two drawbacks of H2O. One is it only supports so far feed-forward topologies, and the second one, it can't be accelerated on GPUs. But if you can live with those two, you can use it in R. If you want to do it, you have to use either Python, Scala, or Java at the moment, or programming language called Lua. There's a framework called Theano which uses Lua. I've never heard that. So what I do is I aggregate on the different axes by ID, and then I basically sum up, and I can do that to calculate the energy, because I'm sampling the accelerator values 10 times a second, and that will then nearly be the same as calculating the integral of that function. And if I then sum up all the aggregations of all x's together, then I get basically the energy everybody produces. So let's do that for that sample data. One second. Okay, and then you can basically just sort the data based on that energy score, and then you get the winner. So that's what I wanted to show you in that demo. And you can run that directly in the cloud, but I'm a bit hesitating now because of the network. But just to give you an idea, yeah, I will do it later maybe. We have a Apache Spark service there in the cloud, and that has IPython notebooks, and there you can run Scala, Python, and R code directly. So you could do the whole pipeline, for example, also in the cloud. Okay, so it was the first thing. So now I want to dive a bit more deeper into analysis of accelerometer data for classification. Oh no, sorry, I think in the agenda we have something else. I wanted to demo you something with deep learning for J on anomaly detection. So actually I've already shown you the results, as you remember here. Let's go back to that screen. This one here, that actually was the anomaly detection done, and I just want to show you how you can do that on your own. So that's Eclipse, and there I have installed DeepLearning for J. So it's a Maven project, so it's a one-liner. I don't know if I can zoom in here. So can you read it in the last? Can you read it in the first row with me? Okay, let's try something different. I will just no, I have a better idea. Let's do it the following. So that was not the correct source code, sorry. So I will now just show you that part here. Is it better? Okay, so you start with network configuration in DeepLearning for J first, and you basically set global parameters of the network. So one is, for example, a very important parameter is the learning rate. So if the learning rate is too low, then it takes a lot of time that you converge to the optima. And if the learning rate is too high, then you will shoot out over the optima and you never get a solution. So that's the parameter you have to tune. And that's what I meant on hyperparameter tuning. So those neural networks, deep networks especially, they have so many parameters. They have parameters which are global to the network. They have parameters on each layer, and also the topology itself is a parameter set. So you get a lot of hyperparameters which you have to optimize as well. So in addition, that training neural networks is computationally intensive anyways. You have to retrain and retrain different topologies and parameter sets, which actually makes it even more computationally intensive. So these are the global parameters, and then you can add layers. So the first layer is the input layer, and the last layer is the output layer, and all the middle layers are hidden layers. And what you basically define here is the number of neurons per layer in the input and in the output. And what you can see here is that between those two, the number of neurons is only 10. And the dimensionality of the MNIST data set is 784, because it's these are images with 28 by 28 pixels, so that resembles in 784 dimensions, what you can see here on the input layer and on the output layer. But in the middle there are only 10 neurons. That actually means the data flows through the deep network, and eventually in the middle of the network the data gets compressed to 10 dimensions only, and that reduces a lot of noise. And that's how you can do anomaly detection. And of course that size of the middle layer is one important parameter which you have to of course find out yourself, which performs best for your data. So then you have the configuration, and once you have the configuration, then you can create a multi-layer neural network. You can create one here. You create it like this. It will create a single node, single JVM neural network, which actually can make already usage of GPUs, because deep learning for J is based on a library called ND4J, which is more or less the equivalent of NumPy, and just on normal CPU with double of the performance of NumPy. but it can run on CUDA 7.5 and be accelerated in GPUs out of the box. So to run this configuration on CPUs or GPUs, you don't have to change anything. Just tell and it's a parameter you set in the ND4J library whether it should use CPU or GPU. But if you want to run this on Spark, Apache Spark, you don't have to change anything in that configuration. The only thing is that you have a multi-layer network configuration where you also pass in a Spark context. And then together with the configuration you get a neural network which is actually automatically parallelized on Apache Spark. So if you have 128 nodes with just the same amount of code, just change 1 or 2 or 3 characters here, you can run the same network on Apache Spark. So that's why I think DeepLearning4J is a very valid option for doing this. So I will just show you then what happens if you have created this network. Then you basically do this. Okay, so I think you can more or less infer it. So your neural network in your brain can actually recognize what these pixels are. So the important line is here, that's net.fit. That actually, so DeepLearning4J is you train a network in batches. So the data is already a batch of data points. And then fit means just use the data and update your neural network parameters. That's per default done by stochastic gradient descent, but that algorithm you can also choose, and you can implement your own optimization algorithms in DeepLearning4J if you found a better one. That's the advantage of doing it object oriented. So it's very easy for you to change plugins in the system. So yeah, then that actually trains the data, the neural network. And training, as I said, means you just update the parameters, the neural network. And then the last important thing you have to do is you say net.score. So there are two important methods beside fit on the neural network. One is score and one is output. Score gives you the lowest reconstruction error. So you have 10 digits, so it's a classification of 10 digits, and for that particular data set it does the prediction, and the class where it has the lowest prediction error is then used to determine the score. So for example, if you have a very weird looking digit, you will get a very low score on that, because it will try to find a class. Let's go back to this one. So for example, if you use the third one, or let's take even go up the very first tracker, it can be 0 or 6. So the neural network will either classify that first digit as a 0 or 6, and then it will return the lowest error score of those two classes. And then what we basically do is here we add all these scores, and then we sort it, and we sort it by the lowest and by the highest, and then you actually get the 5 lowest and the 5 highest prediction errors per class. If you don't want to get a score, you want to actually predict something, you use the net.output method. But we can also have a look later. So that's the anomaly detection part. And now I want to show you something on the accelerometer data as well. So first start with the state of the art. That's not my data and not my idea. I found this in the internet, but actually, to be honest, I had the idea before, and I was searching for data, and then I found somebody who already did the whole pipeline. But that guy did the pipeline using Apache Spark and Cassandra. And if you read through the article, it's not necessary that you use Cassandra. It's just a data store. So I don't know why he used Cassandra. But what he basically does is he is doing the normal state-of-the-art machine learning pipeline, what means he is generating artificial features for the model. So you see here the time series of the accelerometer values, and at a certain point he will tell you, I will zoom in right now, I find the shortcut. So he basically creates 6 different features out of the data. So it's the average or mean per axis. It's more than 6, of course. It's average or mean per axis. So those are 3 additional features. It's the variance per axis, another 3 additional features. Average absolute difference for each axis, another 3 additional. Then that's an aggregation on all the 3 dimensions, and the last one also. So it's 3, 6, 9, 10, 11. He creates 11 features, and then what he does, he uses a random forest classifier, which is already a composite model, and then he basically gets this error rate. So I will repeat this now using R and using deep learning for J, using that data set which has 6 classes. So this is accelerometer data, the one you have created, but it is labeled. So the people have been walking, jogging, going stairs upwards and downwards, and sitting. Yeah, I think those 6. And having that labeled data, you can actually generate a model. And I would consider this 13.2 as the state of the art. So that's more or less the maximum you could achieve. Maybe you can tune it a bit further. So let's start with R and a very little demonstration. So I'm reading that data, and so I'm skipping the division. Normally if you do machine learning, you of course have to divide the data to train and test. And if you do hyperparameter estimation, you divide it into train, test, and validation. But I just skip that because I get the very same error rate on both. So I just calculate 2 or 6 of the 11 features, just for illustration purposes. That's the means of every accelerometer value and the standard deviations. And then I will train a random forest classifier. So now I've trained the random forest classifier. As you've noticed, it's less than a second. And now I will predict. So that's the call here. So I predict classes, and then I calculate the score. And of course I won't get such a good score as we can see here, because I'm not generating 11 features, I'm only generating 6. But let's see what the prediction error is. So training is really fast, and scoring is really slow, for whatever reason. Let's wait another second. And I'm only using those 6 features because I just didn't have time to complete everything else. So as you can see here, I was basically trying to get everything in, but yeah, I most likely will get the same rate of 13.2% because I'm using the same features and I'm using the same algorithm. Just instead of Java and Spark, I use R, but that doesn't make a difference in my opinion. I will know that soon. So, and I just calculate the error rate, which is so the accuracy is 0.32, which is 32%, which is double as good as random guessing. Okay, and I assume that I will get some 86.8% if I use all the features. But that's not what I wanted to show you. Actually, what I wanted to show you is something else. I wanted to show you the same analysis using feed-forward neural network. And as I've told you, a feed-forward neural network is not capable of taking the time or frequency domain into consideration. For that, you would have to use a LSTM or at least a recurrent neural network. But I'm using a feed-forward network, and the thing what this actually does is some sort of creating histograms of the data and using the different bins of the histogram as input values. But I just run this now. So, and I will run it only once, just that it is a bit faster. So now you can see the neural network is training. You see the error rate on the right hand side, and eventually what I'm doing here is, once this is running, I will show you what I'm doing. So first of all, I'm using a 1, 2, 3, 4 layer network, a 2 hidden layer network, and what I'm doing at the end, I'm just calculating the number of times where the network predicted correctly and where it predicted the wrong class. I'm running here on a 70% split, so 70% training data and 30% is test data. And as you can see here, evaluating the model is slower than training the model, but that's just because the training phase is done using ND4J and is running on all cores on that machine, and the evaluation phase is a single thread which I have implemented using plain Java types. And as you can see, as you not can see here because it's too small, let's do it in this one. So without any feature transformation, just feeding in the raw data, I get the accuracy of 0.87, which is higher than the value which has been achieved by that guy, because he has an accuracy of 86.8, and he has done a lot of thinking and pre-processing, and that's the only message I want to tell you. With a deep network, you can basically have the data and the network do the feature preparation or feature transformation for you. Random forest, actually the state of the art, if you consider Kaggle competitions, the state of the art are deeply stacked models, where you have normal neural networks, we have deep learning networks, random forest, gradient, distributed trees or GTMs, gradient distributed, or whatever. So those are the state of the art. Those are already composite models, and they are binned and stacked and so on. And if you do that, you get some sort of 0.0001% more accuracy as the competition, and that will just blow you up 1,000 ranks up. So that's if you do Kaggle competitions now, it's just everybody is more or less in the same percentage of the score, and there's a 0.00 something difference, and those guys are just using stacked models. They are using multiple sorts of algorithms and applying a voting scheme or something, and then just win those competitions. So actually, in my opinion, it's not worth for real life applications. For Kaggle it makes sense, but for real life applications, the state of the art are those random forest support vector machine based models. Okay. So I'm just double checking. Yeah. So that's all I wanted to present. So for those who are interested, I have promised you a hands-on session as well. So if you like, you can repeat this example with your cell phone, and I will show you how to capture the data and how to store it in a relational database and do some analytics on top of that. All in the cloud, all for free in the free tier. And for those who don't want to do that, those can leave after the QA session. So I would now like to open the QA session. So are there any comments, questions, additions? Yeah? Okay, so the most interesting things in that IoT area is the Industry 4.0 transformation, and there the most interesting thing is predictive maintenance. So we actually use sensor data from the machines. We apply vibration sensors, temperature, sound, and we basically use that to predict or to detect anomalies in the manufacturing pipeline. That's the most booming part. Yeah, you need a lot of data for neural networks. So if you don't have so much data, you use the standard ones, which is random forest, support vector machines, or whatever is in the machine learning literature. So the only way to get data is from sensors, or if you are like Google or Facebook or some institution like that. Yeah.
But in US, any use cases are automotive. So, because you mentioned vibration, the sensor, like, easily related to the car.
Yeah. Yeah, it's not on that, it's more on the self-driving side. Yeah. So we are supporting a supplier of a automobile manufacturer in Europe with that technology, and they are coming up with a solution for self-driving cars. Yeah. Okay. 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 Then we have a big Smarter Cities center in Dublin, and a special contract between the city and IBM, so they deliver all sort of data to IBM, and we actually In Stockholm, we can, for example, predict the time you need to travel to the airport at any hour of the day. And in Singapore, some Asian city, we predict the arrival time of vehicles based on weather and the whole system. So, yeah. Yeah. So to everybody I've spoken so far, everybody said it's like experience, because you can't. So far, nobody came up with a optimization objective function, which basically you can minimize. So you have to search through the hyperparameter space, and the only thing is you can try or use some Monte Carlo simulation to find a good parameter set. But that means you have to run the scoring process for each hyperparameter set, and that's very cost intensive. So no solution to that so far. In the Spark context, I run them in sequence, but you could also run. That depends on your credit card, basically. And also for Kaggle, that also if you want to win Kaggle now, you have to have a very good credit card, because it's basically searching through the hyperparameter space, and on that stacked models, the hyperparameter ranks are just exploding. Yeah?
Can I have a follow-up question to this next?
Yes?
So the cover example,
Yeah.
you use historical pattern or use online?
Both, yeah. You use historic and online. So the historic one is for the model, and the online is for the actual prediction.
And the IBM
That's, that I even don't know, it's a very old project in Stockholm. That's even not based on MQTT, I think. It's they are basically putting those devices into trucks and taxis,
Yeah.
and they send the data to somewhere, I don't know where. Yeah. Okay. But I don't have any actual references. The only thing I know is that IBM and Siemens have a partnership, and IBM and Cone have a partnership, and the basic idea is to put that sensors into windows, buildings, temperature, elevators, everything, and get an integrated view of the whole building from all the sensors. And then of course you have a lot of data. You might able to detect anomalies based on all the sensor values. For example, if somebody breaks in, the temperature of one room might change in an abnormal way in comparison to all the other rooms, or the noise level is higher during a very abnormal daytime, and those might be able to trigger an alert. Yeah. But we have no reference use case. We just learn that in future. That's possible. Yeah. Yeah. Yes, so the low-hanging fruits you can always do, and you can just add them to the input parameter set, and if they are not relevant, they get down regulated anyways. Yeah, so you can do that. Yeah, no problem. Yeah, so actually I get the data for presentations from open data sites, because if we get data from clients, we have to sign a couple of NDAs. Sometimes we are even not allowed to speak about the client and the project, and of course never use the data outside of the company. So yeah. No. So Dublin has a contract with IBM, so they are sharing all their data in the case of Stockholm as well. And then it depends. In Switzerland, I'm based in Switzerland, so I went to Zurich and asked them whether I can get some data for prediction, and they said no, just go away. And then I went to Lucerne, which is like a 1 hour's drive, and he said, of course, because all the data is kind of paid by the Swiss population, and you should be able to use it. And he just gave me a DVD with a 10-year history of all the sensors of the city. So that depends. Yeah, but that's the holy grail. You have to get the data, and that's the most important thing, because all that stuff is, you can read it in the internet. All what I've told you is available in YouTube and on websites. You can learn it from there. You can try it your own, but you can't try it if you don't have data. So you see what? Yeah, then now we enter the field of chaos theory. So what you can actually do with that machine learning stuff is you can create transform functions, physical transform functions. But if the function has state, which is the case in the world, so state means if you do the same thing twice, you don't get the same response, because the system has a memory, and then it becomes hard to train a model like that. So that's the question: what if you knew every position of each atom in the universe and you knew every law of physics? Could you predict the future of the whole universe? That's basically that question. Yeah. Yeah. It might be. We have 400,000 employees. I don't know what each of them are doing. But financial markets are falling in that category of chaotic systems, because all decisions in the financial market run through human brains, and therefore it's very hard to predict what happens. You can maybe predict to a certain point, but also the interesting events are very rare, like some crashes. We had like 5 to 10 in history, and that's not enough to train a neural network on. Yeah? That's another discrete parameter. Yeah. No. Actually, I don't notice too much difference. As long it is nonlinear, it doesn't. In my data, it didn't make so much difference. So you have different results. Okay, maybe that depends on. Yeah, we can talk afterwards. Yeah. The benefit. The most I don't know, but one important thing would be, for example, in a self-driving car, if the car could brake and prevent an accident, would be very useful to me, for example. Maybe spread of diseases, something. Yeah, I think there are a couple of very good examples for humanity, but I think the most of them are kind of accelerating businesses there. I'm very, very addicted to everything around machine learning, data, mathematics, neural networks. I'm also very addicted in understanding how the human brain works, and yeah, that's what I do in my free time, and now I do it all day long. I would, yeah, let's say the smarter cities thing is of course also a business opportunity, but also a way to help humanity. I've been working on another project that was not based on deep learning, but it was based on state-of-the-art machine learning, where the goal is to predict in a brain ICU seizures of the brain. And actually the problem there is it's only based on experience. So you have a lot of monitors there, and doctors, they see the data and they have to guess whether they put the patient into CT or not. And if we could predict seizures with a system, let's say 5 minutes before, then you can issue an emergency operation and save the patients. And that's a system actually now in test phase in Zurich, and one patient is already monitored with that. Yeah. LTSM. Yeah, actually the LSTM is trained by sequences of the input vectors, and they have to correlate on the time axis. So you have to ensure that they are coming in the correct order. And you can also, I'm not an expert on them, but you can also trigger them that they forget, and then, for example, get the data from the next user. For example, in that accelerometer data, I would just feed in data from one and then from the next. But yet the basic idea is you have the same input like in the feed-forward network, but you have you feed them in sequence, and that basically resembles the time domain. Yeah. Yeah. Excuse me, what did? I didn't understand the last sentence, sorry. Yeah. Okay. There I cannot tell you because the current version of deep learning for J supports only a generative LSTM network. So in order to, that's also the reason why I implemented it with a feed forward, because there is no LSTM available for classification at the moment. So I assume it's higher because you are considering time and frequency with such a network. Yeah. And actually, that rate, what we see here, is also not taking time and frequency into account. So you could even push that value higher. Yeah? Yeah, I don't forget the data, I forget the memory. So there is a memory, there are memory units, but I don't forget the parameters. So basically, by training neural network, I'm learning parameters, which I've shown you before. But what I forget is the memory in a subset of the neurons, because I want to start from scratch and I want to see the new sequence as a time series, and that's why I trigger the forget button of the network kind of. Yeah, that depends on the order. If you have another order, then you get another parameter. Get other parameters. They are slightly different. And what is done is we introduce some random order of the training. So we do multiple times. So you can see, it doesn't matter. You train the network multiple times with the same data. So that's called epochs. And in each epoch, random number generator shuffles the order of the training data. And for example, if I run this example again, then I get another value. I will get 0.87546 instead of 87547 or something, because based on randomness, the parameters will differ in each run. Yeah. Yeah. Yes. So it's a so-called tumbling window. Yeah. I'm not sure whether you can use other windows. No, sorry. The tumbling window is the point where you trigger the forget. Okay, and a tumbling window is what you said. It's just let's say 10 examples and then next 10, just sequence or batches. It's batches, tumbling window. And sliding window is where you actually fed in the data which is consistent in the tumbling window. And on each, so if you trigger the forget button of the network, so all the memory units are cleared in the network, and then the sequence of data will come in, and then data will be remembered in that tumbling window, and therefore will result in different parameters as you wouldn't have the memory. And if you then, that's one way of doing it. You just on each tumbling window occurrence you trigger the forget. But as I said, I'm not the expert on LST. I'm just yeah. Yeah.
Seems like simulating human brain will only be a matter of time. Does IBM at the roadmap for what they want to achieve in how many years and where they want to go from? I mean, obviously they will eventually reach the goal of simulating human brain. Is there any roadmap that you start really want to build with the neural network?
So first of all, I can say we are not trying to simulate the human brain, because you can forget that at the moment, because to really simulate a neuron in the brain, you need, for one neuron, you need let's say one laptop, because a neuron is not just what you see in the artificial one. A neuron has chemical properties, so the synapses have chemical properties. The whole brain is neuromodulated, so that's basically what more or less you can say state of mind. So if you are in a very relaxed mood, your brain functions completely different as if you are stressed, and all that stuff is not able to be simulated with that kind of neural networks. So where they are good is in pattern recognition, perception, and IBM has on the roadmap to transform IBM to a cognitive company. And in my opinion, there's only one competitor or two, that's Google and Baidu. And only Google and IBM at the moment have a hardware accelerator for neural networks. The IBM one is called True North, and the Google one is called TPU, Tensor Processing Unit. Tensor is another name for a multi-dimensional array. So I think those two are making the race at the moment. And the only asset what Baidu has is Andrew Ng. Maybe you know this guy. You should Google for him. He was basically co-developing the Google Brain 2009, and then he got pissed off because Google was not giving him 1,000 GPU cards within one day. And then so he was coming from Stanford, he was a professor at Stanford, then he went to Google, and now he went to Baidu, and they gave him that. Now that he is experimenting with 10,000 GPU cards. So that means he now has the power of 10,000 times the Google Brain 2009. Yeah? Yes? Yeah, it's my presentation. I just go back to that slide. Maybe I was going too fast on that one. You was, okay, no problem. I just give you, those are those two slides. So that's the 2009 Google Brain, 16,000 CPU cores, 1,000 nodes. Then 2016 NVIDIA Titan GPU card has the same computing power, and the hardware accelerator of IBM has the same one like those two and consumes 4 watts. Yeah, it's an ASIC, it's an application specific integrated circuit. It doesn't have a clock, so the data is just propagating through the units without a clock. Yeah, it can only run, at the moment it can only run feed-forward neural networks. And what you basically do, you configure the connections between the neurons, which are called synapses, by updating memory units on the chip. And for example, you configure the activation function. There are some where you can choose from by updating a memory unit on the GPU. Basically, you can flash the topology of a feed-forward network, including the parameters, into such a chip. No, you have to update it. It's field programmable.
Oh, I see.
Yeah, it's like a FPGA for neural networks.
How about
That's hard to say because they are not disclosing it. So there are some rumors. The Google one seems to work on a lower level. So maybe you have heard Google released a software called TensorFlow. And the tensor, as I said, is a multidimensional array which is basically used a lot in neural networks. And they are accelerating the calculations on tensors. So that's all what we know. The rest we don't know the internals of the chip. They have used it in DeepMind, the one who won against the Go champion, to accelerate computation. And in my opinion, it's only my opinion, Google released TensorFlow because they want everybody to use TensorFlow, and then they keep the TPU in their cloud. And if you really want to accelerate your pipelines, then you have to go to the Google Cloud. Because I don't see any plans that they will sell it or redistribute it or revend it. And in the IBM case, that roadmap is also not very clear, but I have heard that IBM is talking to end clients and integrating the chip in their system. So I think it's a bit more open, but let's see. But it's a different architecture for sure. Maybe, yeah. Yeah? What do you do with categorical what? Yeah. I'm just thinking whether I have ever used some. I would use Google and see what others do with that. Yeah, I don't know whether. With me? Yeah. Yeah, but in my opinion, at the moment, I have to read a bit about it, but I would say it should work out of the box, because no, categorical not. If they are ordinal, it would work, but if they are categorical, I would have to read a bit about it. There's a word-to-vec example also in the DeepLearning for J distribution, so you can try it out. Okay. No more questions? So I would say we just skip that hands-on thing, because 25 minutes is not enough anyways, and I just stay here. Maybe we have some face-to-face discussions and more relaxed atmosphere. Okay? Thanks a lot.